Good morning, everybody. This is Math 0310, March the 8th. It's the last day before spring break. Yay. A couple of announcements. Web-assigned homework. I've been trying to make announcements about this every lecture. For those of you who are watching the recorded version of this, 9.5, 9.6, and 9.7, those three sections are due March 18th at the end of spring break. And then the 9.8, section 9.8 and the section on complex numbers is due a week after that on March 25th. I will not be extending those dates, so please be working on the homework and getting those assignments done. Some exam 2 information. The review is posted. So, and I posted that earlier in the week. So you've got, and it's again a lengthy review, lots and lots of practice problems, and it's a good review of the material that's going to be on this exam. So please be looking at the review and be working on that over spring break. The window for exam 2 is March the 22nd through the 27th. And then I'm going to be on campus the week after spring break, March 21st and 22nd. Right now, I think my hours are going to be 4 to 6 on the 21st and 9 to 11 on the 22nd. I'm not 100% sure of that, but I'm pretty sure that that's where they're going to be. And if there is a change to those hours, I would definitely let everybody know ahead of time. I am available over spring break by appointment. So if you have a time over spring break and you're having some questions about something on the homework, on WebAssign, or on the exam 2 review, do not hesitate to send me an email or a remind message, and we can make an appointment sometime over spring break. I can get with you and help you out. So don't hesitate to do that. Remember, also no lectures are posted next week at all, just like on my calendar. That's the way it's indicated. So nothing happens as far as new material over spring break at all, but I will be available for online help if you need it. Today, we are moving into solving quadratic equations. We're leaving square roots, which is in cube roots and exponents and everything, so that's probably good. Most people do not enjoy that chapter particularly, and so we are moving into solving quadratic equations, which is one of the reasons why we were talking about exponents and radicals, was because of these methods for solving quadratic equations. So that's where we're headed today, into chapter 10, and we'll finish up chapter 10 next week. Remember, there is, when I say next week, I'm sorry, the week after spring break when we come back, the Tuesday after spring break, we'll pretty much finish solving quadratic equations. Remember that this material right here is on exam 3. I'm stopping exam 2 with complex numbers, which is what we covered on Tuesday of this week. So the quadratic equation stuff, 10.1, 10.2, and the rest of chapter 10 will be on exam 3. Okay, so kind of keep that in mind. All right, so first of all, let's talk about quadratic equations. We've talked about quadratic equations already this semester, and we've encountered quadratic equations periodically throughout the semester. Don't forget that a quadratic equation is a second-degree equation in the form ax squared plus bx plus c equals 0. That's the general form. We just know that the a can't be 0, so in other words, there has to be a squared term in the equation for it to be a quadratic. My college algebra students run into quadratic equations constantly throughout the semester in all sorts of different places, and they need to know how to solve quadratic equations. There's no question about that at all. Now, the method that we've talked about so far, what we've done is we've looked at using factoring to solve a quadratic equation. Using factoring actually, and the property that when you have two numbers multiplied to give 0, that the only way that could be true is if one of the two numbers was 0, right? So we call that the zero factor theorem. And so using factoring and the zero factor theorem, we could solve some quadratic equations. So x squared minus 2x minus 3 equals 0, was an easy factoring problem. X minus 3 times x plus 1, set each factor equal to 0, and you solve the equations. And you get the solutions to the quadratic pretty quickly, just 3 and negative 1. 4x squared minus 25 equals 0. Same kind of problem, right? It's a quadratic, and factors is the difference of two squares, 2x plus 5 times 2x minus 5. And then again, you set each factor equal to 0 and solve each of those equations. This is not a big deal. Now, some of you still have a little bit of problems with the factoring, especially with harder trinomials. But most of this has become, I think, and I've gotten that impression in class, is that most of you have gotten to the point where this is relatively routine to do stuff like this and to solve these types of equations using factoring. 3x squared minus 15x equals 0. Sometimes this throws students for a little bit of a loop, but remember, you take out a common factor first before you do anything else, and then you set each factor equals 0, and you get the solutions. So here you get 0 and 5 as solutions. So this is not a big deal. But there's a big problem looming here that we've not really talked about too much. We've mentioned briefly in class, but there's a big problem here, and the big problem is not all quadratic expressions factor. In fact, if I were to make up a quadratic expression kind of randomly, so even something simple like x squared plus 2x plus 2 equals 0, it's not factorable. And so the factoring method and the zero factor theorem are useless in this case because there's no way to break this down as a multiplication problem and to solve the equation using the zero factor theorem. It just doesn't work. And so when it's not factorable, that's the question, is now what, right? That's basically the question is, now what do you do? And so that's what today and the Tuesday we come after spring break, that's what this is all about, is to talk about what do you do in a case where the expression is not factorable. Then how do you proceed to solve the equation? So when I say now what, there are 3 other methods for solving quadratic equations. And those 3 other methods are the square root method, which we will talk about today. The square root method only applies when you have an equation in the form something squared equals a constant. The equation has to be in the form something squared equals a constant in order for you to use the square root method. And I said square method. I kind of left out an important word there. Square root method. There you go. All right, so the square root method applies when you have an equation in the form something squared equals a constant. The second method is called completing the square. And completing the square always works on any quadratic equation. It always is something you can use. The problem is with completing the square is it does always work. You can solve any quadratic equation by completing the square, but it can be a messy method to use. It can be a very messy method to use. And then finally, the last method is the quadratic formula. We're going to actually derive a formula for solving a quadratic equation, and we can solve any quadratic using this quadratic formula. It's actually a formula. It's like the area formula for a circle or the area formula for a triangle. This is a formula that will allow you to solve any quadratic equation. So it always works also. Again, it can be kind of messy to use. Not as messy as completing the square, but it can be messy. So what we're going to do is we are going to cover these first two methods today, and then the quadratic formula and then some word problems we're going to cover when we come back after spring break. Okay, so so the square root method is our first stop here. And the square root method, like I mentioned above, only works in a situation where the equation is in the form something squared equals a constant. So what we're going to do is we're going to talk about some very simple equations that are in that form and outline the method for solving using this method, and then we'll extend it to more difficult problems. See, so if you have something simple like this, x squared is equal to 25. I want you to think about that for a second. X squared, you're trying to solve that equation. You know, what are you doing here? You're saying, well, what numbers, when I square them, would give me 25 as an answer? And there are two solutions to that equation, right? Because there's two numbers you can square to get 25, because 5 squared is 25, but negative 5 squared is also 25. And so this equation has two solutions. It's 5, but it's positive and negative 5, like that. All right, if you had x squared equals 100, it's the exact same deal, isn't it, right? That you've got two numbers that you can square to get 100. Two real numbers that square to give you 100. It's 10, but also negative 10. You can square both of those and get 100. So this equation has two solutions also, positive 10 and negative 10. Now, in both cases, what did you end up with as the solution? You ended up with the square root of 25 and the square root of 100, right? The solutions to the first equation were just the square root of that number that you started with there. And one way to look at this is that when you have an equation that's in this form, x squared equals k, that what you're doing in some ways is you're taking the square root of both sides of those of that equation. You're taking the square root of both sides. And the square root of x squared would be x, and the square root of k, you get square root of k, and then you just have to remember that there are two solutions, and so you put a plus or minus in front of the constant there. And so what you're doing here is you're taking, in words, this is the way we're going to describe it, taking the square root of both sides of the equation. And then you have to remember that there are two solutions to equations like this, and so you have to remember the plus or minus also. And so this is kind of outlining the method right here. Now I've got it written for x squared equals k, but it will apply in more complicated situations, as you'll see as we go through this. All right, so let's look at some more equations in the form x squared, or something squared equals a constant. So if we had x squared is equal to 12, right, then we could take the square root of both sides of the equation. And by the way, one thing I didn't mention as we're going through this, but these are obviously quadratic equations, right? This is a quadratic equation. Now, it's not written in a general form, but these are our quadratics that we are solving. It's just that they're in this nice special form, something squared equals a constant. They have an x squared term. They are second degree equations, right? So these are quadratic equations. They're just not written in this nice ax squared plus bx plus c equals 0 form. They're written in this more specialized form, something squared equals a constant. So that's what this problem, this is written in that form, something squared equals a constant. So if we take the square root of both sides of the equation, then the square root of x squared would be x, and then over on the right side we'd have the square root of 12, and then we have to remember to put a plus or minus there, so you get plus or minus the square root of 12. And then one thing I'd want you to do is use what we've talked about back in chapter 9 and simplify these kinds of square roots. So the square root of 12 we know breaks up as the square root of 4 and the square root of 3. Right? We've done a lot of simplifying like that now over the last week or two of the semester. So you have plus or minus 2 times the square root of 3, like that. And those would be the solutions. In this case, these are irrational numbers. We talked a little bit about that, but these are irrational numbers because they have a square root in the answer like that. If there's no square root written in the answer, then the solutions are rational solutions. These are what we call irrational solutions. Okay, so that seems easy enough. So let's say we have x squared is equal to negative 36. Now, we're solving these equations over the complex number system, so I'm asking you to find all solutions. Find all solutions. And so when I say find all solutions, I'm talking about real and imaginary solutions. Now, in some WebAssign questions, they simply ask you for the real solutions only. So you have to kind of be aware of that a little bit when you're solving these. This particular equation, x squared equals 36, has no real solutions. But when I take the square root of both sides of the equation, right, I get the square root of negative 36 there, and I get plus or minus. And we talked last time about the fact that the square root of negative 36, the square root of a negative number, is imaginary. Right, so this is plus or minus 6i. Don't forget that the square root of negative 1 is equal to I. Right, so you're using that to simplify this problem. This is the square root of 36 times the square root of negative 1. So we replace the square root of negative 1 with I. So remember, the square root of negative 36 we would write as 6i. So the solutions in this case, these are imaginary. That's okay. I'm going to have you find imaginary solutions. Would be plus or minus 6i. Okay? Let's say we have x plus 6 quantity squared is equal to 20. X plus 6 squared is equal to 20. All right, now the expression that's being squared is a little bit more complicated on the left side, but it still is just something squared, right? And so we can take the square root of both sides of the equation, and we get x plus 6 on the left side. In the right side, I get the square root of 20, and I don't forget that it's going to be plus or minus the square root of 20. Really easy to forget that plus or minus. I mean, I get calculus students sometimes that are forgetting that plus or minus. So you need to know that anytime you are taking the square root of both sides of the equation, you've got to put a plus or minus in front of the constant. All right. So now what you should do at a point like this is simplify the square root of 20. Remember, don't break it up as 2 and 10 because 2 and 10 are not perfect squares. We talked a lot about that in the last chapter. So you break it up as 4 and 5. So the square root of 4 is 2 times the square root of 5. And then you have not solved for x yet, so you subtract 6 from both sides of the equation. Now a little bit of a notational thing here. You know, we're subtracting 6 from both sides of the equation. Do not write it this way. Do not write plus or minus 2 square root of 5 minus 6. It's not wrong to write it that way. Definitely not. And I would never penalize you for doing that. But it gets tricky as to whether that 6 is underneath the radical or not. Because, you know, sometimes the radicals are written a little sloppily. And it can be difficult to figure that out. So what I would prefer you do is I would prefer you stick that negative 6 on at the beginning as a term and write negative 6 plus or minus 2 times the square root of 5. I'd rather you put it that way. So those are the same thing. These are the same. I would not penalize you for writing it the second way, but this is what I would say is the preferred way for you to write it. It would be like this. Stick that negative 6 in at the beginning. And then the negative 6 and the 2, don't forget, you can't add those because the 2 is multiplied to the square root by the square root of 5. And so, in fact, those are your solutions right there. It's just negative 6 plus 2 times the square root of 5 and negative 6 minus 2 times the square root of 5. Sometimes in WebAssign, they'll ask you to enter solutions like this, but they'll ask you to enter it as a comma-separated list. So you have to pay attention to WebAssign and what they're asking you to do as far as writing these. And so in that case, you'd have to write this as negative 2 minus 2 square root of 5, comma, negative 2 plus 2 square root of 5. Right? You'd write it in that as a list like that. All right, let's see. Let's say we have x minus 4. Put another example right here. X minus 4 squared is equal to, let's say, 49. All right, so what you do, take the square root of both sides of the equation, just like we did before. That's no big deal. So you have x minus 4 equals plus or minus the square root of 49. Now the difference here is the square root of 49 that's a perfect square, so you end up with plus or minus 7. And then add 4 to both sides, so you get, and I'm going to put the 4 at the beginning, like I said a minute ago, so you get 4 plus or minus 7. Do not leave it like that, though, because this is a problem where you can do the arithmetic. So if you can do the arithmetic, you should finish this. That is something I would penalize you for, because now you're just being lazy, right? So I don't leave it as 4 plus or minus 7. You write this as 4 plus 7 and 4 minus 7 and finish the arithmetic. So you get 11 and negative 3. Right, 11 and negative 3 are the solutions there. Right, if you have a radical in your solution, then you're not going to be able to completely do all the arithmetic, okay? But if all the radicals drop out like they did in this problem, then finish it. Don't leave it as 4 plus or minus 7, something like that. All right, let's see. Let's go to another example. So this one we have 2x plus 3, quantity squared, minus 50 equals 0. 2x plus 3 squared minus 50 equals 0. Now this equation, don't forget that we talked about in the square root method that you had to have something squared equals a constant. Well, this one is not in that form because the thing that's squared is not equal to a constant, right? So you need to write it in that form if you can. So this would be 2x plus 3 squared equals 50, right? Just add 50 to both sides. And now all of a sudden the equation is in the form something squared equals a constant, all right? So now we take the square root of both sides of the equation. Now you're allowed to go that route, and you get plus or minus. Don't forget the plus or minus, the square root of 50. I would simplify the square root of 50 before I did anything else. That breaks up as the square root of 25 and the square root of 2. So you have 2x plus 3 equals plus or minus 5 times the square root of 2. And now you solve the equation for x. So you subtract 3 from both sides. So that gives me 2x equals, don't forget what we said on the last problem. Go ahead and put that minus 3 at the beginning so it's not confused with being underneath the radical. And so you have negative 3 plus or minus the square root, 5 times the square root of 2. And then we are not done yet because we've got to solve for x. Right? So you have to divide both sides of the equation by 2, so you get x equals, and I would just leave the right side as a fraction and have negative 3 plus or minus 5 times the square root of 2 over 2. And so the solutions to that equation, a little bit messy. These are irrational solutions, remember? And so you get negative 3 plus or minus 5 times the square root of 2 over 2. And those would be the two solutions to this equation. This is not that bad. I really don't think so. So let's say we have 5 times 4x minus 7 squared plus, let's say we have 40 equals 0. Okay, let's have a look at this one. So to solve this using the square root method, it's got to be in this form something squared equals a constant, which this one's not. So you've got to do that first. Get the thing that's squared by itself. So the first thing we do is we subtract 40. Right, get the constant over to the other side of the equation. And it's still not in the form something squared equals a constant. We would divide both sides by 5. And so now you've got it in the form something squared equals a constant, right? 4x minus 7 squared equals negative 8. And now you take the square root of both sides of the equation. So on the left side, the square root of 4x minus 7 squared would be 4x minus 7. And on the right side, you get plus or minus, don't forget that, the square root of negative 8. And because you're taking the square root of a negative number, this is going to be imaginary, right? Break this up as the square root of negative 4 and the square root of 2. So you have 4x minus 7 equals plus or minus, and the square root of negative 4 is imaginary. It's 2I times the square root of 2. And now you can solve the equation pretty quickly for x. Add 7 to both sides, which gives you 4x equals, put the 7 at the beginning, 7 plus or minus 2I times the square root of 2. Don't be tempted to add the 7 and the 2 together, because you'd be violating order of operations if you did that. And then as the last step, we would divide both sides by 4, and we get 7 plus or minus 2I times the square root of 2, all divided by 4. Right? And so you get a pretty messy looking solution, 2 imaginary solutions here. Right? And we have solved this equation using the square root method. So not too bad, not too bad. All right, so what we want.
I have a question.
Oh yes, please, Raina. Yes.
Where did you get the I? I don't see a negative 1.
Don't forget that right here in this step. Okay, good. That's a good question. You have the square root of negative 4, and don't forget that the square root of negative 4 is really the square root of 4 times the square root of negative 1, right? There is a square root of negative 1 in there. And then the square root of 4 is 2, and square root of negative 1 is I. Right, so anytime you get a negative underneath the square root, you're going to end up with an imaginary solution there, because you can always take that negative 1 out as a factor, right? Does that make sense?
Yes.
Okay. All right, so yeah, so that will come up again, definitely. So anytime you see a negative underneath the square root, you're going to have a square root of negative 1 in there, and so be prepared for that, definitely. All right, so now let's look at what happens if the equation is not in the form something squared equals a constant. So if it's not in the form something squared equals a constant, can you still use, there's a way to force it to be solvable using the square root method. So let's write that out. So if an equation is not in the form something squared equals a constant, there is a way to force this, to always, in fact, force the equation into this form. And this technique is called completing the square. So completing the square is a way to take any old quadratic and force it to be in the form something squared equals a constant, even if there's doesn't appear to be any way that that's possible to do. So let's look at an equation like that. So let's look at several equations like that and walk through how we complete the square here. So let's say we have this equation, x squared plus 6x plus 7 is equal to 0. All right, so now this equation, you cannot put this in the form something squared equals a constant just by moving terms around. See, like if you subtracted, maybe you'd say to yourself, hey, I could get the x squared by itself. Well, that's true. You could subtract 6x and subtract 7 and get x squared equals negative 6x minus 7. The problem is this is not in the form something squared equals a constant form, right? Because there's not a constant on the right side of the equation. You've got an x over there. So that's not a way to use the square root method. It's not going to work right there. So what we're going to do is we're going to force the issue here. We're going to complete the square to do that. And completing the square will allow us to actually put the equation in the form something squared equals a constant, and then you use the square root method to finish up the problem. So what you always do here at the beginning is you move the constant to the other side of the equation. Move constant to the right side of the equation. Now notice when I did that in this step, I also left a space where the 7 was. Okay, so we're going to fill in that space with something else. So what you do, and this is the critical part to completing the squares, this next step, is you take the middle coefficient, whatever it is. I'm going to write the arithmetic out off to the side here. You take that and you multiply it by 1/2. In other words, you take half of that middle coefficient, which is 3, and then you take that answer and you square it, and you get 9. So this is a two-step process right here, right? Those two steps always go together. You take 1/2 times the middle coefficient. The middle coefficient in this problem was a 6, so you take 1/2 of 6, which is 3, and then you square the 3 and you get 9. Now that constant that you end up with, the 9, you end up adding that constant to both sides of the equation. So I add 9 here, and because I've added 9 to one side of the equation, I have to add 9 to the other side of the equation also, right? Whatever you do to one side, remember you have to do the same thing to both sides, right there. So you add that constant to both sides. So you add constant to both sides. Now what happens here is that the left side always factors when you do this. The left side always factors, and it factors as something squared. Always, always, always. It's always a perfect square trinomial. That's why you pick that constant in the right way. You take half of it, the middle term, and square it. And this is how it factors, by the way. There's a nice little pattern to this. So I'll put the parentheses down with a square here. And simply the square root of the first term, the sine of the middle term, and then the square root of the last term. It's always the way it's going to factor. So you can count on that always being the case, because you're using the pattern of a perfect square to get that, that constant term when you set this up. On the right side, just add the -7 and the 9, and you get 2. And see, now you can use the square root method. So now use square root method. Right? Because now you have the equation in the form something squared equals a constant. Right? And we've actually forced it, right? We've taken the original equation. Here's our original equation right here. And we've rewritten it so that it is in a form where we can use the square root method. And we completed the square to do that. So now you just take the square root of both sides of the equation. You get x plus 3 equals plus or minus, and this would be the square root of 2. And then subtract 3 from both sides. I'll put the 3 at the beginning. I get -3 plus or minus the square root of 2, and I have solved the equation. And so the solutions are -3 plus the square root of 2 and -3 minus the square root of 2. Okay, so this is we've outlined the step. Now there's one step we'll have to add to this little method we've outlined here, but completing this square, I'm going to highlight that right here, involves moving the constant to the other side of the equation, like we did here, And then you take half of the middle coefficient and square it. You add that constant to both sides of the equation. And now you factor, right? It always factors as something squared. And then you use this square root method to solve what you have what the form you have the equation in. So it's always going to be following that format right there. All right, so with that in mind, let's go ahead and work another problem. And please stop me. Raina had asked about the 6x. And the 6x, when we move the constant, we're literally leaving the 6x here. So, Raina, I don't know if that was your question or not, but that 6x gets left here, definitely, because you need the middle term in order to be able to complete the square. Without that middle term, you couldn't complete the square, because you couldn't get the square of a binomial that would factor that way. So that 6x has got to be left there when you move the constant. All right, so I don't know if that addresses your question or not, but. All right, so let's look at another example. So let's say we have x squared minus 10x plus 29 equals 0. All right, so x squared minus 10x plus 29 equals 0. Once again, no way that you could solve this using the square root method just like it is. So we're going to complete the square to solve this equation. All right, so we complete the square. All right, so to complete the square, what do we talk about? We take the constant and we move it to the other side of the equation. So and I leave a space also. So I subtract 29 from both sides and I leave a space. Right? And I always leave that space because I want to emphasize that I'm about to add something else to this side of the equation. And so now our steps. You take the middle term. By the way, it doesn't matter that it's a negative 10. That is not a big deal because we're going to square the number as our next step. So I kind of ignored the sign at this point because it doesn't matter because the second step is you square the number. It's always positive. So half of 10 is 5. 1/2 times 10 is 5. And then you take the 5 and you square it, and you get 25. That is the constant I add to both sides of the equation in this next step here. So I've got x squared minus 10x equals negative 29 like that, and then I'm going to add 25 to both sides of the equation. So add 25 to the left side, and I add 25 to the right side. Probably the single most common mistake students make is to forget to add it to both sides of the equation. All right, and so now the left side of the equation is factorable, right? This always factors as the square of a binomial. And in this case, since the middle term is negative, it's going to be something minus something. And so this is the way this factors on the left side of the equation. It's the square root of the first term, so that's x. The sine of the second term, that's minus. And then the square root of the third term, that's 5. So it's x minus 5 squared. And on the right side of the equation, you have negative 4. Negative 29 plus 25 is negative 4. And see, now you've got this equation written in a form where you can use the square root method to solve it, because now it's in the form something squared equals a constant. So we take the square root of both sides of the equation. So the square root of x minus 5 squared is x minus 5. Don't forget the plus or minus over here, and this is the square root of negative 4. And then, Raina, you asked about this a few minutes ago. It's the square root of negative 4. Remember, that's the square root of 4 times the square root of negative 1, or 2i, right? So you have x minus 5 equals plus or minus 2i. So the solutions to this equation are going to be imaginary. And then add 5 to both sides, and I have 5 plus or minus 2i. And those are the solutions to this equation, right? And so the solution set is 5 plus or minus 2i, like that. Now, by the way, I didn't talk about this, but certainly you can check this. Don't forget, you can always check, even though they're imaginary. So let's check x equals 5 plus 2i. There's two solutions there, 5 plus 2i and 5 minus 2i. So I'm going to check 5 plus 2i. So this is x squared minus 10x plus 29 equals 0, right? That's our equation. Every place I see an x, I put 5 plus 2i. So I substitute 5 plus 2i every place I see an x. And believe it or not, this is going to check. When you do all the arithmetic on the left side, you're going to get 0. So 5 plus 2i squared. Don't forget that you're squaring a binomial there, so that's this little pattern we've talked repeatedly about, right? So that first term is going to be a 5 squared, and then 2 times 5 times 2i, and then a 2i squared. That's the 5 plus 2i quantity squared right there. And then multiply through by negative 10 right here, and that gives you negative 50 minus 20i, and then plus 29 equals 0. So let's see where this leads us. You get 25. The arithmetic is messy. There's no question about that. Plus 2 times 5 times 2 would be 20i. Plus 4i squared. Don't forget that I squared is equal to negative 1, so we'll do that in the next step. And then minus 50 minus 20i plus 29 is supposed to equal 0. Geez. So you have 25 plus 20i. I squared is negative 1 right there, so this would be minus 4, because it would be 4 times negative 1. And then minus 50 minus 20i plus 29 equals 0. So let's see what happens. The 20i's add to give 0. And then let's see, you've got the negatives, negative 54 and 25 and 29, positive 54. Everything drops out, and you're left with 0 equals 0, and it checks. I'm not going to ask you to check something like this, but I'm just pointing out that you definitely could check it if you wanted to, and it would never be a problem if you find yourself on an exam in a situation where you've got time. Check your solutions, see if they actually work, right? If you're worried about a problem, go ahead, a quadratic equation, solve the quadratic, and then check the solutions, and you ought to be able to check it. All right, let's see how we're doing on time here. We're doing great on time. You're going to. This is not going to be as long a lecture as we typically see, definitely. Let's look at another problem now. Let's say we have 3x squared minus 12x plus 7 equals 0. 3x squared minus 12x plus 7 equals 0. All right. So remember what we talked about. We talked about moving the 7 over. Now this problem does have an extra step to it. So I move the 7 over. The problem is you cannot complete the square in this form. The coefficient of x squared must be equal to positive 1. And so if it is not positive 1, then what you do is you divide every term by whatever that coefficient is. What we're doing is we're dividing both sides of the equation by that number. Every term gets divided by that number. So the 3's divide out there, and you get x squared minus 4x equals negative 7/3. Sometimes this leads you to an equation with fractions in it, and there's no way to avoid it sometimes. All right, so now we complete the square, right? So we take the half of the middle coefficient, half of 4 is 2, and then we square 2 and we get 4. And so 4 is the constant I add to both sides of the equation. I'm going to add 4 to the left side, I add 4 to the right side, like that. Okay, and then we factor. Don't forget that this factors a nice little pattern. It's something squared. It's the square root of the first term, sine of the second term, square root of the third term. Now on the right side of the equation, you've got some fraction arithmetic here. This is negative 7/3 plus 12/3 right there. So you have x minus 2 squared is equal to 5/3. And then you go ahead and square both sides, take the square root of both sides of the equation. So you have x minus 2 equals plus or minus the square root of 5/3. Now you can solve that easy enough by just adding 2 to both sides. You get 2 plus or minus the square root of 5/3. And that would be fine. Typically, you're not going to see the solution written in that form. Typically, like in WebAssign, they're going to go ahead and probably rationalize that fraction so that there's no radical underneath in the denominator. So they're going to multiply numerator and denominator over here by square root of 3. So that gives you x equals 2 plus or minus the square root of 15 over 3. Remember, the square root of 3 times the square root of 3 is 3. And, probably you're going to, in the textbook, for example, you will see a common denominator between these two fractions, which is 3. 2 and 6/3 are the same thing. And so you're likely to see this as 6 plus or minus the square root of 15 over 3. Now notice that looks nothing like the original solution. Right? The original solutions we got look like that. And at first glance, it doesn't look like they're the same at all, but those are the same number. Most times in WebAssign, you're going to see that last form like that. I would probably want you to rationalize the answer, but I would accept that form right there. But you have to be careful to go by the rules that your college algebra professor outlines next semester, and they may tell you that they, what form they want, and they may only want it in that very, very last form. So you just have to pay attention to what they're asking you to do. Okay, so just to kind of give you a heads up on that. Okay, so let's look at one more problem with the completing the square. Let's say we have x squared minus 3x minus 8 equals 0. X squared minus 3x minus 8 equals 0. All right, so we don't have to worry about there being a coefficient at the beginning, so that's good. So we can just move the constant over, and we're ready to complete the square. The only problem here is that when you multiply that middle term by 1/2, notice you get a fraction. You get 3/2. Sometimes you're stuck with that. There's no way to avoid it. So you just go on with the problem. You square 3/2 and you get 9/4. So 9/4 is the constant that I am going to be adding to both sides of this equation. I'll add 9/4 here, and I'll add 9/4 over here. Sometimes there is just no way to avoid the fact that you're going to be adding a fraction when you use this method. Half of 3 is 3/2, right? And so once you got that fraction like that, you're kind of stuck with it. Don't do anything different. Just makes the arithmetic a little bit messier. So you have something squared here. This would be x minus, right? There's a square root of the first term, the sine of the second term, the square root of the last term, which would be 3/2. So this is x minus 3/2 squared equals This is 8 over 1 right here, so you get 32 over 4 plus 9 over 4. And so I get x minus 3 halves squared equals 41 over 4. Okay, and then you take the square root of both sides of the equation. So you have x minus 3 halves equals plus or minus the square root of 41 fourths. And the good news there is the 4 is a perfect square. So you could just write this as plus or minus the square root of 41 over 2. And then add 3 halves to both sides, and you've solved the equation. Right, so this would be 3 plus or minus the square root of 41 all over 2. And those would be your solutions.
I have a question.
Yes.
Where are you getting the 32 over 4?
32 over 4. Okay, so Taylor, when I added those two together, you know, I had 8 plus 9 fourths. So that's really 8 over 1 plus 9 over 4. Right, and I got to get a common denominator. So on the 8 over 1, I'm going to multiply that by 4 over 4.
Got it.
Right? So that was just to get a common denominator right there.
Okay.
Anybody else have a question? Okay, then you know, that's it for lecture today. We wanted to solve using the square root method. We wanted to solve using completing the square. And so, like I said, this is kind of a shorter lecture today. Next time what we're going to do is we're going to look at the quadratic formula and derive the quadratic formula using completing the square, kind of go that route. So I do want to write some textbook practice down here. We're back to the elementary algebra textbook. And this is page 1147. This is section 10.1. And really any problem from 15 through 45 would be great practice right there on that page. Actually through probably 51. So let me erase that. And then on section 10.2, not as much there. I'm going to, the square root method is going to be more important for us. Let's see, 10.2. Oh, there it is. Okay. So 10.2, this is on page 1163. And this would be problems 60, let's see, so it would be 69 through 81. Not as many of those. So, okay. So, does anybody have any questions to finish up class today?
No questions. No questions.
Okay. Well, then for all of you guys that are with me live right now, anybody who's watching this recorded later, do not hesitate to email me if you want to try to set up an appointment over spring break. I'll try to work something out with you. Have a great spring break. Remember, I don't have any regular office hours next week. So, so if you're going to try to find me anytime over these next 9 days or so, it's got to be by email or remind. I will be checking those on a relatively regular basis. So, okay?
Okay, sounds good.
Excellent. You guys all take care, and I'll be in touch, definitely. Have a great spring break.
Okay, you too. Thanks.
Thanks.
Okay.